Okay, so I hope everyone saw my post on D2L before. The situation is I have a pretty major health crisis going on in my family. So on Monday, I couldn't give the lecture live, but I did post a video on D2L to a past lecture that should be as good, if not any better, than my usual lectures. So you won't have missed anything, along with the lecture notes. And so, as possible, I'll do that in the future if I have to miss another day. But generally, class is going on as normal, and I want to be sure that you know that you can always email me, and we can set up office hours as usual. Nothing is changed. Are there any questions about anything before we dive in? All right. What's going on here? Is someone? Okay. Like someone was unmuted. Okay, so are there any questions? Okay. In that case, I'm going to start from where the video lecture I provided to you left off, which was in the middle of a lecture on the Milky Way. Now, kind of where that lecture left off was reminding you that when you look out at the Milky Way, right, in the sky, you can look out at the sky and you see this beautiful band of kind of milky white color due to just literally billions of stars all kind of so far away. It just looks milky, but you see these dust lanes going across the sky, right? And these are interstellar clouds of gas and dust that can absorb light, so it obscures your view of the Milky Way. But it's also where new stars are born. New stars are born from this interstellar medium that includes gas and dust, ultimately produced mostly from stars that previously lived and died. Okay, what's going on? Okay, before I move to the interstellar medium, I'll ask you one poll question from the last lecture, because I couldn't. The last one was a video lecture. So let me pull that up. Find it. There we go. So let me go to the polling. Oh, that's not it. Halo. I want it. Not be able to even find it. There we go. Okay, so polling. Okay, so right, one thing that was covered in the last in that video lecture was what kind of objects lie in the halo of our galaxy. We talked about different components of our galaxy: disk, the central bulge, and the halo, kind of the whole almost spherical region. And be careful not to just assume everything is there. There's something that's by far the most common that's there. That's this question is.
I think of this one. I think it's that one. That young big blue.
I'll give you 10 more seconds. Okay. And it looks like most people did get the right answer, so that's great. Globular clusters. So we talked about how in the disk of our galaxy, first of all, that's where there's a lot of new star formation. That's where you see that gas and dust. There's lots of new stars in the disk. So there you would see B, hot, young, blue stars, maybe, for example, and gas and dust. You'd also see what we call open clusters. Globular clusters is primarily what we find in the halo of our galaxy. Those are those giant clusters of millions of stars. Okay, so let's then go back to where we left off, which was interstellar medium. So this is the stuff that exists between all the stars in a galaxy. Gas and dust, okay. It's mostly gas, right? Just about 1% of it is dust. And that gas is mostly hydrogen, right? It's the same thing that our sun is mostly made of, and our solar system is mostly made of. Remember, it's always mostly hydrogen, next helium, and then little bits of metals and stuff and dust. And so on average, the number density, we say that the number of particles per cubic centimeter in the, we would call it the vacuum of space, because there's very few particles, but there's still some particles. It's on average about half of a particle, half of a molecule per every cubic centimeter. And in comparison, in normal air, it's like a trillion times more, okay? But the interstellar medium can range, though. It can range from like a 10,000th of a molecule up to 1 million molecules per cubic centimeter. And the more dense regions are where you have maybe star formation, okay? So when talking about what makes up the interstellar medium, we're talking about gas and dust, okay? And over large regions of the space between stars, space is huge. So even though it's like, we might call it the quote unquote vacuum of space, there's a fair amount of molecules out there, and over light years, it adds up to a huge amount of matter. In fact, most of the matter in galaxies is in the interstellar medium, in gas and dust, not in stars themselves. Here's just some examples. So like air is about 3 times 10 to the 19th molecules per cubic centimeter, which is about 100 or 1,000 times less than like what's in water or diamond. So that's, we're getting up to like a trillion molecules per cubic centimeter in this region. Down here in the interstellar medium, there's no such thing as a perfect vacuum. So you can have very good vacuum, which we call hot bubbles, because when you heat something up, things move away from each other. The vacuum becomes better. So in what we call hot bubbles, there can be only maybe 100th on average of a molecule per cubic centimeter. In the Milky Way, on average, it's about half a molecule per cubic centimeter. But places where you might have star formation, you might, or just places that are fairly common in the interstellar medium, called molecular clouds, might have, a few hundred molecules per cubic centimeter on average. And so, yeah, there's these different regions we can talk about. We can talk about places that are bubbles that are hotter on average, and so have fewer molecules per cubic centimeter. This is our local bubble. Here's the sun, and there's these regions where a long time ago there were supernovae, and supernovae heat up the surrounding region. Okay, so on average in our local bubble, there's about 0.05 atoms per cubic centimeter. But there are regions like the, if we zoom out even further to the local interstellar cloud, it becomes a little bit larger, maybe 1/3 of an atom per cubic centimeter on average. That's not zooming outward, that's just a local cloud, I should say, near us that does have more or on average. Okay. Here are some of these regions that are kind of highlighted in yellow, where we can locate the previous supernovae that happened millions of years ago. Supernova here, that have created these bubbles of region that's been heated up by that supernova, and so has kind of expanded outward into the interstellar medium, leaving a lower number density. Of course, over time, that's going to cool down, and then it'll contract again, and then you'll have more stuff from all that stuff expelled from the supernova will form what we'll talk about, nebulae that can form stars in the future. And it's just kind of an interesting observation. You might note that throughout, the Earth's history, there have been relatively nearby supernovas happening. And our galaxy is very large. Supernovas are happening all the time, and supernovas that happen close by kind of irradiate us. In fact, if the supernova happened too close, it could destroy everything on Earth. Right? Remember, these are really powerful explosions. But there's been some relatively nearby supernovae that we can see in the geologic record. For example, there were some very close, notable ones around the time when humans, when Homo habilis, the speciation of humans into the type of human that became Homo sapien, kind of branched off from the kind of earlier hominids that never became. Of course, we think very highly of ourselves, but became intelligent, thinking people, right? And one could speculate that this has to do with the supernova increasing the radiation on Earth, therefore causing lots of DNA mutations and speeding up evolution. And so that's just speculation, but it's just something you can think about, that when we talk about these things like supernovae, talk about hot bubbles that are the result of supernovae locally, this is the sort of thing where it actually does relate to you. It relates to the evolution of humans. It's because it can change the DNA mutations, change the course of evolution. So like really, really big supernovae that are kind of consequential to us tend to happen every million years or so, as you can kind of see in this record. Of course, astronomers would be really excited to see one it's close by a supernova. And if you saw one like one of these, it could become very, very bright in the sky, like right in the middle. Okay. Now, when we look out at the interstellar medium, we can look at it, not all the time with visible light, but there are different types of interstellar medium that emit different types of light that we can characterize based on their temperature. Now, most of the interstellar medium is hydrogen. So let's talk about the three types of hydrogen we see in the interstellar medium. Okay, there's molecular hydrogen. That's what happens when it gets cold. If it gets so cold that instead of seeing individual atoms, the hydrogen snap together to form H2. And in this case, you can quote unquote see these molecular clouds through radio waves and infrared radiation. Okay. If you get more towards room temperature, you have what's called neutral atomic hydrogen, just hydrogen atoms, single hydrogen atoms. That's what you normally think of as hydrogen. And in that case, I'll talk about it. There's a very specific radio line of wavelength 21 centimeters, like this long, that allows you to see it through radio telescopes. And then if you get closer to a star where the hydrogen is kind of ionized, hot, so a few thousand degrees, say, then you get these transitions in the atoms we'll talk about that can emit very specific spectral lines. The most famous of which is red, called the H alpha spectral line. Let's go through these. The H alpha comes from the fact that, remember when we talked about atoms are governed by the rules of quantum mechanics, you have these energy levels, And if an atom is hot enough, the electrons can move between energy levels. And these are various energy levels electrons can move between. And here's the famous third energy level to second energy level transition that gives off a red light. Okay, and so when we look at interstellar space and we see red lights coming from kind of cloudy regions, that's interstellar medium that's glowing due to being kind of warm. Now, there's another neat thing that allows us to detect more room temperature hydrogen, which is that the energy, so similar to here where you have hydrogen electrons going between different energy levels, it turns out that for atomic hydrogen that's not ionized, you can, instead of transitioning the electron from different energy levels in the atom, you'd actually just flip the spin. Now, electrons have this thing called spin, and you can have the electron spin flip up or down, and that changes the energy a little bit of the atom, corresponding to this very low energy radio photon that has a wavelength of 21 centimeters. Okay, so this actually means that these clouds at room temperature are constantly absorbing and emitting light at this very specific temperature, or at this very specific wavelength. So this is how we see with radio telescopes kind of room temperature hydrogen clouds. Okay, so what produces the 21 centimeter radio line? We call it a line because if you look at all the light coming from the sky, you see a bump at 21 centimeters in wavelength because it's something you commonly see. It's caused by atomic hydrogen. Okay, so that's kind of room temperature interstellar medium. And where we're going with all this is that there are nebulae, these beautiful kind of clouds of gas and dust where star formation happens, and that's often produced by dying stars that we can kind of look at and understand what we're seeing based on what I just talked about. So nebulae, these are interstellar clouds of gas and dust. Some of it's just the primordial, meaning just hydrogen and helium from the Big Bang, but also it's a lot of material ejected by stars, whether from a dying low mass star or a supernova remnant from a dying high mass star. And what we can do is we can look at these, and there are three main characteristics of these nebula that we can classify them by, and I'm going to show lots of pictures. If you have gas and dust that's kind of warm and glowing, we can see the light from these. These are called emission nebula. If you have gas and dust that's reflecting nearby a light, that's called reflection nebula.
Reflection?
These aren't emitting light of their own, it's just reflected light you're seeing off of clouds. And then there's also absorption nebula that are kind of darker, they absorb light. And in most nebula, it's some combination of all three, okay? But some have one that's more prominent than others. So I'll show you some examples, okay? Emission nebula are kind of glowing, ionized, hot. You see a lot of red from that hydrogen alpha line I talked about. So anytime you get warmer gas in a nebula, we call this an emission nebula because it's emitting light. So often if you have a nearby star, it can cause the gas to be ionized, warmed up, and then it emits, for example, that hydrogen alpha red light. Here are some examples, but we'll look at some particular examples. There's a particular nebula called the Retina Nebula, very pretty one. This is mostly an emission nebula. Okay, here's a nebula called the Lagoon Nebula. Here, there's a very classic color, this kind of red color from this glowing gas, mostly hydrogen, that is an emission nebula. It's a kind of a stellar nursery. It has this open cluster. So you see these blue stars. These are kind of young stars that just formed. They're kind of heating up this gas, and so then it's emitting this red light. Nebulas are often associated with stars being born, and we can sometimes we would call those a stellar nursery. Here's a very famous nebula called the Trifid Nebula, where you actually have all three emission, reflection, and absorption going on at once. So you have emission in purple, pink here. This bluish color is reflected light, okay, reflected light. And then you have these dark bands that are absorption regions, right? This is colder gas and dust that's absorbing light. Now, there's some nebula that are mostly just what we call an absorption, or I mean, a reflected nebula that are mostly blue. They're mostly blue, one, because you're often reflecting light from young stars that have just been born, that are often blue in color, because remember, short-lived stars are the brightest stars, and they are the hot blue stars. Also, dust tends to reflect blue light more strong. A really famous example is the Pleiades, which if you look up in the sky at night, on a nice dark night, you'll see like kind of a fuzzy patch of a bunch of stars that are so close together, it almost looks fuzzy. But another reason why it's a little fuzzy is it's a nebula. You can see those kind of bluish clouds of reflected light kind of making it fuzzy because you're seeing clouds. It's a reflection nebula. Here's another famous one, Witch Head Nebula.
Which head?
Okay, here's a reflection nebula where you're also seeing lots. So you're seeing this blue, but you're also seeing a lot of absorption. So this dark, colder gas and dust is absorbing light. You also see a little red over here. So there's a little emission. This is in Orion. And then absorption nebula. These are ones that are most characterized by their absorption. So dark interstellar clouds which obscure our vision, so we can't see through them. So here's a very famous one called the Eagle Nebula. Here's the Horsehead Nebula that's in Orion. If you look near Orion's belt, take a long exposure photograph. This one kind of looks like a horse head. You also see some reflection and some emission in red here is going on as well. If you zoom out from the Horsehead Nebula, what you see is Orion's belt. So these are the three stars in Orion's belt. Here's that Horsehead Nebula, and here's the Horsehead right down here. Now, one interesting thing is if you look at these in say infrared, you can see different features. So here is in infrared, the Horsehead Nebula. What you see is that these clouds that are dark and visible light, they're absorbing light, they tend to be warm enough that they, they're not hot, but they are emitting infrared light. Okay, so they show up in the infrared. Okay, here's the Eagle Nebula, where you can see some of these. I just showed this earlier. These beautiful and famous features. I'm going to zoom in on some of these in a second. Eagle Nebula. These are called the Pillars of Creation. Very famous. Here they are zoomed in. The Pillars of Creation, which are a part of an absorption nebula. These particular thick clouds of gas and dust that make it so you can't really see through them. But you can see their edges are sort of glowing because nearby stars are heating up their edges, causing them to kind of essentially boil off some of that cold gas and dust. So Veil Nebula. Now, one thing that we see a lot, or one thing I need to point out, is that a lot of these nebulas are produced from supernovae. So it's a supernova remnant. You can imagine a supernova exploded, and this is the kind of expanding gas and dust kind of expanding away from that supernova, producing a nebula called the Veil Nebula. There's a piece of it. It's also called the Witch's Broom. So like there's a piece, very beautiful. You see in blue reflection, you see in red emission. Here's another example. It's a 40,000-year-old supernova remnant. We can really clearly see in the center a supernova went off 40,000 years ago. and you have this expanding kind of cloud of material. And in these regions, as they cool off, they begin to collapse, and you can form new stars. Here are more like earlier after a supernova. This one supernova went off just 500 years ago. You can see it in its early phase of expanding, this kind of giant explosion in space that went off. You see different colors because some of it's an X-ray, but it's still really hot, emitting X-rays. Here's a Crab Nebula that went off about 1,000 years ago.
Crab?
Expanding outward. You see really all things going on in here. You see reflected light, absorption, and emission. And kind of what we see in the galaxy is stars live and die. And that material doesn't just go away. We call it galactic recycling. Gas. Stars return gas back into interstellar space. First of all, while the stars are alive, they're kind of producing these stellar winds, kind of ejecting material out into space. When low mass stars die, they kind of shed off all their outer layers, producing what we call planetary nebula. And then there's supernovae, high mass stars, produce these really big explosions, but that also distribute all sorts of material. In that case, a lot of heavier elements too, and out into the, that's where all the carbon comes from, all the iron and so on, is distributed out into interstellar space. And then this stuff all mixes back into the interstellar medium where there's extra hydrogen. And that stuff cools off over time, and you form molecular clouds. So next you form these clouds that are colder, that are emitting radio waves. And then the stuff condenses under gravity to form stars again. And so it goes full cycle, okay? So here's, let's look at some spot here, okay? So here is a star. Here is a star, okay, in the lower left. There's a little bubble around it. Why is there a bubble around it? It's interstellar wind pushing out into the interstellar medium. So, so it's emitting stuff already into the interstellar medium. Then it dies and it produces a supernova.
Oh.
That supernova pushes stuff out into the interstellar medium, which cools off. And then we see it as atomic hydrogen clouds, okay, through radio waves. And we see it as molecular clouds through radio waves. And then finally, star formation begins in these denser regions, like these places you might call stellar nurseries. Then stars form. We went through the whole process of explaining how stars form. Nuclear fusion begins, and the cycle continues. That's the star cycle, or galactic recycling. And essentially, this just keeps happening. The only thing that changes, something does change. So over time, right, as stars live and die, they are fusing elements. So you're starting out with hydrogen. Well, you keep fusing hydrogen into heavier elements. Now remember, most of the material in a galaxy is in the interstellar medium. So there's plenty of hydrogen to keep forming new stars. But over the star-gas-star cycle, you keep increasing heavier stuff and using up a little bit more and more hydrogen. So over time, you get a little bit less hydrogen, more heavy elements. So, okay, yeah, so here I'll ask a question about what I just talked about. Okay, so what happens after many generations of stars living and dying in the star-gas-star cycle?
What happens? I think it's this one.
I'll give you 10 more seconds. So good. Most people got the right answer, which was that over time, the amount of heavy elements, carbon, the stuff we're made of, iron, oxygen, silicon, all these heavier elements are increasing over time in the galaxy. The amount of hydrogen slowly decreases.
Also E. Okay.
Because of all this chaos going in my life, I'm gonna actually go quickly answer the door. Sorry. Okay, looks like I didn't actually have to answer it. Okay, so yeah, most people got that right. So fantastic.
E.
Okay.
Okay.
Any questions so far? Okay. Here's a nice picture of well, like an illustration of galactic fountains. Okay, that is, if we try to map out, say the Milky Way, we can see regions. So here's the sun shown. We can see regions where there have been these supernovae that heat up the interstellar medium and cause material to be kind of ejected out into more of the halo of the galaxy, which then slowly, due to gravity, rains back down. So you can call it sort of like a fountain, a galactic fountain.
Interesting.
It's kind of beautiful looking. But this is part of this process of the galactic star gas cycle. You can kind of see stuff getting pushed out from. This is where most of the gravity is pulling right into the disk, because that's where most stuff is. Stuff gets pushed out in the interstellar medium, and then it can kind of rain back down into the disk, where eventually it cools down, forms new stars after it mixes in with all that hydrogen in the interstellar medium. And one cool thing, because remember, this is the stuff where planets, like terrestrial stuff, us with carbon comes from, right? We wouldn't be here if it weren't for the fact that stars have lived and died before us, right?
I'm in class, man.
If we actually look at regions, like here, I introduced this before.
I'm still in class. Get
out,
yo.
You can actually look out, see what's in there. And this is the stuff that's mixing into the interstellar medium that's going to form new stars in the future. What's in there? There's all sorts of interesting stuff. And we can see it by using spectral analysis, right? We basically, as I described before, you basically send the light through a prism, and what you see is, in this example, you see a lot of this particular purple color corresponding to oxygen. Okay, you see this particular bump in a red color corresponding to sulfur. You see neon. Okay, you see hydrogen, of course. You see some nitrogen. Anyways, you see all of these heavier stuff that was produced in that star, right? That as that star fused hydrogen into helium, and that helium into carbon, and then into oxygen and nitrogen and so on. You see all that stuff coming out into the interstellar medium. I talked about the stellar wind, which adds to the interstellar medium. It's just a really cool example where you see this in extreme cases where you have a really big star. So there's a 45 solar mass star, type O. So remember, OBAFGKM. Type O stars are the bluest, biggest, hottest stars, and they have a huge, really strong solar wind. So out here is the interstellar medium, but you see this kind of bluish bubble where that solar wind is kind of pushing out, pushing against the interstellar medium. Okay, it's called the bubble nebula, because that wind is so strong that it's creating a nebula. Here's another image of the same thing. It's about 10 light years in diameter, this bubble. Okay. Orion is a really interesting place. So here's a full picture of Orion. If you can't tell, here's like the upper left. These are the arms here. There's the belt, sword, the legs. So it's Orion on side. But if you do a really long exposure photograph of Orion, you see all this beautiful features. So in red, right, this is Mission Nebula. You see some blue from Reflection Nebula. Remember, hidden down in here is the Horsehead Nebula, so this absorption nebula. And there's star forming regions here. We call part of the Orion Nebula is like a 2,000 mass. So if you add up all the mass in it, it can form like over 1,000 stars. Okay, and it's going to become an open cluster in the next 100,000 years. That is a cluster of hundreds of stars, for example, in this region around Orion, especially near his belt. And by the way, if we, just like we talked about for that supernova remnant, if we look, now here's a nebula where it's now actively forming stars. What's in it? Well, we can do spectral analysis. Again, we kind of shine the light through a prism, we see what it's made of, and we see all sorts of fascinating stuff that's like the precursors to life, okay? Things we would call organic molecules, things like methanol, hydrogen cyanide, sulfur dioxide, methanol, sulfur, I mentioned sulfur dioxide, formaldehyde, carbon monoxide, water. All these things that you see that are organic, these are things involving carbon that are sort of the things that were probably present on Earth.
Twice?
There's another star forming region about 3,300 light years in size. You have some star forming in this Great Carina Nebula, which is kind of, you see these really beautiful features. Let's see if there's zoom in. Yeah, you see these like little islands of absorbing kind of colder dark gas. So this is absorption nebula region, but they're being warmed by nearby newly formed stars. And as they warm up, it's almost like if you toss some water on a hot stove and it's sizzling, it's kind of evaporating around the edges and they're going away. Million years. Okay. Where will most of the gas be in about 1 trillion years? Well, over trillions and trillions of years, eventually you're using up all of the interstellar medium, okay? And you're going to be locking a lot of this material into white dwarfs. Now, remember, a white dwarf is formed after a low mass star dies. And remember, low mass stars are by far the most common type of star. And remember, when supernovas explode, they can leave behind neutron stars and black holes, but they're far less common. Far more common, low mass stars produce white dwarfs. And then there's really low mass stars that can sometimes live as long as 1 trillion years. Okay, so over time, you're going to be recycling in the galaxy for billions and billions of years, but eventually, you're going to be left with lots of these carbon cores, these white dwarfs, these stellar remnants, and then some orange, long-lived, low-mass stars. The Milky Way, right? We're still kind of talking about the Milky Way, our galaxy. Of course, this is the only place we can study nebulae. All other nebulae in other galaxies are too far away. We can study from all sorts of wavelengths of light. So here's now, if you look just invisible light, let's see if I can move this because, yeah, invisible light shown here, in other words, optical, this is what it looks like if you look up at the night sky, right? If you try to look towards the center of the galaxy, where it'd be the bright central, it's obscured. You see all this gas and dust. But luckily, we can look at all sorts of different wavelengths of light that allow us to just see through it, okay? Here's in the infrared, so different types of infrared allow us to kind of see that central disk. If you look, remember we talked about molecular hydrogen. Allows us to look in the right. We can use radio waves, for example. This whole region is all different wavelengths of radio waves, allowing us to see different aspects of different types of gas, right? Depending on its warmth, right? So remember, again, we have hydrogen, you have a little bit warmer hydrogen that emits like some red, well, ionized hot hydrogen emits some red, and then you have something in between, just atomic hydrogen that emits specific 21 centimeter. You can go the other direction. You can look at X-rays. That's where you begin to pick out, you know, really, really hot objects, maybe things like black holes and neutron stars. Similarly with gamma rays. And I want you to remember just some of these basics, like we talked about the 3 phases of the interstellar medium. One of them was molecular clouds. What is a molecular cloud in this case? It's made of hydrogen. It's hydrogen molecules. Okay, a molecule means multiple atoms together. In the interstellar medium, remember, it's mostly hydrogen. So here we're talking about H2, okay, in molecular clouds. Now, how does the galaxy evolve over time? We talked about galactic recycling, and each time stars live and die, they're fusing these elements into heavier. Okay, but then it mixes with the interstellar medium, which is mostly hydrogen. But then when you form new stars, there's a little bit more of that heavy stuff like carbon, stuff like oxygen, stuff like iron floating around in stars. We call this the metallicity. Okay, so like the fraction of hydrogen is given X. Maybe it's 99% hydrogen. Usually it's a little less because you have lots of helium. So then there's a fraction of helium. And then Z, the metallicity, is the fraction of metals. So for example, something common would be about 73% hydrogen, 25% helium, 2% metallicity. And what happens is the metallicity increases over billions of years because stars live and die. And when they die, they shed out heavier elements that they've fused from hydrogen. So I think I mentioned before the population of stars. There's 3 populations. There's metal-rich stars that tend to be mostly in the disk component of our galaxy, because that's where stars are living and dying. So stars in the disk of our galaxy are now about 2% metals on average. 2% stuff heavier than hydrogen and helium. If you look out in the halo of our galaxy, where you have those old globular clusters, we call this population 2. These are much older. They tend to have not undergone very many life-death cycles, so they can have just a small fraction of a percent of metallicity. And then there's a population of stars that don't exist anymore, called population 3. Those were the first stars that formed right after the Big Bang, that didn't have any metals, because in the Big Bang, the only things that formed were hydrogen and helium mostly. And the only way we have other things is through stars. Now, we can kind of understand something about the evolution of the Milky Way by looking at, for example, these halo stars that have very small percentages of heavy elements compared to the disk stars, which have lots of heavy elements. And the difference is that in the disk, you have stars living and dying a lot. So what we can understand is that our galaxy probably formed from a giant cloud, gas and dust. Halo stars formed first, okay? But because there's not, because gravity caused this stuff to contract and form this disk with most of the matter, there's not a lot of stuff out in the halo to keep allowing stars to live and die. What you have left, all the younger stars have died off, and what you have left are these really old, small, orange stars that have low metallicity. But the stuff that's settled into that disk, the stars keep forming. There's a lot of stuff in there. So you get lots of younger stars that looks a little bit bluer. And this also tells us, over time, what's going to happen eventually in the Milky Way. You're going to be using up all that hydrogen, helium. You're going to be, all your bluer stars are going to die off because they live short lives. And you're going to be left with an orangey Milky Way, billions and billions of years in the future, as more and more things that you're left with are just hard to see white dwarfs and these long-lived, low-mass orange stars. And of course, what will happen over time is higher and higher metallicities. Compared to our sun, most of the stars in the halo of our galaxy are older. Okay, in order to be old, you have to be red. Okay, and because what this corresponds to are low mass stars. Low mass stars are red. Low mass stars live a long time, and that means they're pretty dim. Okay, you look at the HR diagram. The red stars are low in the plot, meaning they're not very bright. Okay, and they don't have very many heavy elements because they've lived so long. They haven't resulted from newer from many first and best stars. It's the kind of story I want you to
halo stars
away
are
with.
all not bright.
Where does star formation occur in the Milky Way today, right? This is the sort of thing I want you to know quickly. In the spiral arms, right? That's the disk. What I mean here is the disk of the Milky Way. And the spiral arms is where you can see that there's lots of stuff. That's the densest part, okay, of the disk, or in the spiral arms. Now, what's in the very center of our galaxy, right? It looks like, if you look towards the center, it overall looks like there's more stuff. It looks brighter, although remember, optically, it's kind of covered in a lane of dust. So it's a little hard just with our eyes to see what's going on in the center. But it's also something to remember is space is huge. So even when you look towards the center of the Milky Way and it looks milky white, like there's billions of stars that must be getting so dense. If you actually went there, it wouldn't look all that different from around here because stars are so far apart. Okay, space is so huge that even in the center of the Milky Way, if you zoom in, it looks kind of like this. Okay, so this is zooming in the direction of Sagittarius, and for that reason, we call this region Sagittarius A. In Sagittarius A, this is the center of the galaxy here. What this particular picture is showing is that the center of our galaxy looks kind of normal, but you do have a lot of emission stuff. I mean, a lot of light in various forms. You have a lot of radio waves. Here you're seeing examples of X-rays that are emitted as I'll talk about. We suspect there's these central black holes that are gobbling up material, emitting flashes of X-rays. And here we're actually seeing something got gobbled up and flashes of X-rays that are kind of echoing, reflecting off things that are being shown in this image. But kind of what I wanted to show you here in some sense is that the center of our Milky Way, if you zoom in, there's just a bunch of stars. Okay, it's not super different, as best we can tell, from any other place of the galaxy. Just overall, there's more stuff. And there does seem to be some particular specific region that we call Sagittarius A star that we identify with what we think is the supermassive black hole at the center of our galaxy, somewhere in here. Here's another picture. This is in radio waves. So there's a lot of radio waves being emitted from the center of our galaxy. So in radio waves, that's kind of the center of Sagittarius A star, where we think the central black hole is. Now, you're not seeing the black hole here. What happens is you just have all sorts of material around and near the black hole that's emitting light. Okay? You're definitely not seeing the black hole itself in any sense. Okay, here's a radio, it's another radio wave image. This is 10 light years in size, showing a region around Sagittarius A star, the central supermassive black hole, where there's just basically a bunch of material that's kind of orbiting and maybe falling into this region.
What do you want? I'm in class. Go away.
Yeah, here's another good picture. Just this is
go away. I'm in class.
Also, so this is the mosaic, so it includes both infrared and just optical, showing just, the stars near the very central region of our galaxy. And it's kind of unassuming, right? This arrow is pointing to where Sagittarius A star is, where we think this supermassive black hole is at the center of our galaxy. Some of these look brighter just because they're closer to us. And if we map out, but now one big piece of evidence that there's a black hole here is if we map out over time the orbits of these stars. There's the stars. We watch the stars' orbits. Here's some example orbits where we take snapshots over and over again, and we watch the stars orbit. They're all orbiting around something. And we can use Kepler's laws, like we've described before, to figure out exactly how massive this thing is that they're orbiting. Okay. What we've learned, so first of all, this region at the center of the galaxy is about 26,000 light years from us. And these orbits of these stars are orbiting around something that's less than the size of Uranus. Okay, so it's almost like the planets in our solar system are orbiting, but these are stars. The stars near the central black hole are orbiting around something that has to be smaller than our solar system. And from Kepler's laws, we find that whatever they're orbiting has more than 1,000,000 times the mass of our sun. So first of all, whatever they're orbiting can't be a star. Remember, a star can't be more than 150 solar masses. So it's some object that's super massive, over 1,000,000 times more massive than our sun. Basically, if this were a black hole, it would be very hard to see because for something that's massive, all that mass just needs to be inside a region that's about 0.08 astronomical units. So less than the orbit of Mercury. Okay, is where all that stuff needs to be compacted in order to have your event horizon and represent a black hole. Now, we don't know anything that could possibly explain this unless this was a black hole. Okay, this is just a reminder, something I might ask you on the quiz. Where does the galactic center lie? Where is this supermassive black hole at the center of the galaxy? Well, if you want to locate it, it's in the direction of the constellation Sagittarius. Okay. Of course, if you can see the Milky Way, you kind of see that just by looking at the Milky Way. But it's in the direction of the constellation Sagittarius, and as a result, we call it Sagittarius A. What kind of object do we think lives at the center of the galaxy?
A black hole.
A black hole that's a few million solar masses, right? So more than 1,000,000 stars worth of mass, all in a tiny, tiny region, where we see stars are orbiting this region. That's whatever the region is, it's less than the size of our solar system. Okay, any questions about the Milky Way? Any questions at all? Okay, if not, I will start talking about galaxies more broadly. If I can. So, of course, the Milky Way is one galaxy, right? It took a while for people to understand this. This actually was, less than 100 years ago, actually, when we actually realized that other galaxies even existed. People just, because it takes a really good telescope to see, it looked like there's these fuzzy blobs. People couldn't tell how far away those blobs were. They thought they might be like nebulae. In fact, they originally were called nebulae. Clouds. It wasn't until, and we'll tell the story of Hubble determining the distance to Andromeda that we actually learned that the universe was way bigger than we previously knew. And in fact, for the first time, we really got a full picture of this in the 1990s when the Hubble telescope went up and could take a picture like this. Now, these are one of the most remarkable types of pictures in all of astronomy. Where the Hubble telescope went and just took a picture of what looked like a completely dark, tiny, tiny pinpoint of the sky. This is just a tiny, tiny point. You took your, like a tip of a pen and pointed it at the sky. It's like that region, some dark region where it looked like there were no stars. Went and sat and stared and took a long exposure photograph for about a month. And this is what came back. Thousands of galaxies. Okay, so in every tiny point of the night sky, there are thousands of whole galaxies, each with billions of stars. They are varied. They look different. Here, you can think of them as islands of stars. You see little spirals, like little pinwheels. You see little fuzzy blobs. You see some that look orange, some that look blue. Here's a really fuzzy orange blob. Here's that you see kind of cigar-shaped ones, and things that look like kind of a sprinkler wave. Anyways, it's amazing. Each one of these has billions of stars. Okay, so this is the world of galaxies. We can look at, study, and catalog all sorts of galaxies. One interesting thing to understand that becomes important when you talk about galaxies is that light is very fast, okay? But remember, the nearest star to us, it takes 3 or 4 years for light to reach us from the nearest star. So if we look at the nearest star, if we look at the nearest star, we are seeing it as it was 4 years ago. Now, for galaxies, they can be billions of light years away from us. So when we see a galaxy, we're seeing it as it was billions of years ago. So if we imagine galaxies all formed around the same time after the Big Bang, one kind of confusing thing to get your mind around is like if you look at a picture of galaxies, which one is the youngest? Okay. Well, the youngest galaxy is the one that's farthest away. Why? Because you're seeing it as it was a really, really long time ago. So when we talk about galaxies, we have to actually start talking about time a little bit. Because a billion light years away means that you're looking at something a billion years ago, as it was then. All right. Now, when I show you that picture of all of those galaxies, people since Hubble's time have noted some various different types of shapes. So Edwin Hubble was the first to classify these in a way that stuck. The main types of galaxies we call ellipticals. These look like just kind of fuzzy objects that can be very spherical or can be kind of more cigar shaped. And then there's the spirals, and there's 2 main types of spirals. Okay, there's these what you could just call spiral galaxies, shown on up here on the top of what kind of looks like a tuning fork diagram. And on the bottom, these are called barred spirals. So these are like spirals, but they have kind of a cigar-shaped bar in the middle. Okay. And of course, in reality, you can have all in-between shapes. So this is the main types of galaxies we see. The main thing to understand is that elliptical galaxies are like what exists at the center of spiral galaxies. Okay, you can have kind of a spherical elliptical galaxy surrounded by kind of this whirlpool that's a spiral galaxy. You can have kind of an elliptical, like cigar-shaped elliptical galaxy at the center of a spiral galaxy, in which case it looks something like this. You'll see all sorts of pictures, but here's just the more complete with actual photographs from the Space Telescope,
Ooh,
kind of showing you all these examples. So these are examples of elliptical galaxies. They look like kind of fuzzy blobs. Here are spiral galaxies. They look kind of like pinwheels. Here are barred spiral galaxies. Like here's a nice example of one. It almost looks, I like to think of it as like a sprinkler, and one of those sprinklers that's shooting out one on each side and whirling around. And then you have in-between types of galaxies. And then you also have just irregular galaxies that just don't fit into any category. And so I'll show you examples of these. The nomenclatures that use S for spiral, SB, capital SB for spiral and for barred spiral. Okay, spiral galaxies have a big disk component, right? We're talking about the disk of a galaxy. Spirals, the thing about spirals is they have a disk. Elliptical galaxies are like if you took a spiral galaxy and removed the disk. All that's left is this fuzzy blob that was at the center. So elliptical galaxy, we say it only has the spherical component of a spiral galaxy. Lenticular is just somewhere in between spiral and elliptical. And then you have irregular galaxies. So these are all types of galaxies we will talk about. So just remember that there's ellipticals, there's spirals, there's irregular galaxies. No such thing as a globular galaxy. There is such thing as a globular cluster, but that's stars, okay? No such thing as a globular galaxy.
Galaxy.
So let's look at some pictures of spiral galaxies. So first, here's the cartoon. So we talked about this for the Milky Way. If you take a side view of a spiral galaxy, you have the disk. The disk tends to be bluer. It's where there's lots of star formation happening. That's where most of the material is.
you have this central bulge that, as we talked about, if you kind of stripped away the disk and just left the bulge, that would be an elliptical galaxy. Okay, but spiral galaxies are like our Milky Way. Our Milky Way is an example of a spiral galaxy. And then a part you don't really see too much visually is the halo. There is stuff extending out spherically outside of the disk region called the halo of any galaxy. And there's all sorts of sizes and shapes of galaxies. Our Milky Way has 200 billion stars. That's kind of a fairly ordinary example. About 100,000 light years in diameter. Its disk is about 1,000 light years thick. Overall, it has about 1 trillion times the mass of our sun's mass. This is kind of typical of the galaxy. So as I was saying, right, a spiral galaxy has a disk, because the flat kind of pinwheel-looking shape. You often see that's pinwheel shape because you have these spiral arms. We'll see pictures. And then in the very center, you see this kind of fuzzy bright bulge. Okay, that's called the bulge. It's a group of densely packed stars at the center of the galaxy. Then you have this extended spherical halo with older stars in it, such as globular clusters. There are subgradations. So this was Hubble's classification. If you look at a spiral, so that's given S. If it's got a really big central bulge and really tight arms, we call it SA. But on the other end of the spectrum, if it has a very small bulge and it's mostly just a big flat pinwheel, we call that SC. Additionally, about something like half of all spiral
Hello,
galaxies have
Manny.
a central bulge, this kind of cigar shaped. We call these barred spirals. Okay? And in that case, we use capital S, capital B, for barred spiral. And they have the same thing. You can have barred spirals where you have a really big central bar, all the way to barred spirals where it's mostly just that thin, flat, pinwheel part of the galaxy. So here's an example of a spiral galaxy without a bar, so just a normal spiral galaxy. It's SB, so it has a significant central bulge, which you see here. Has spiral arms. You can see these dust lanes. And whenever you look at a galaxy, remember it's three-dimensional. Here you're kind of seeing it not straight on, not side view, kind of like slanted like this. This is the Andromeda Galaxy. It's the closest major galaxy to us. Nice example of a spiral. By the way, there's these two little ellipticals. I have a whole section just on ellipticals, but Andromeda has two little satellite galaxies. They're these little fuzzy blobs. Those are examples of elliptical galaxies. Here's a nice spiral galaxy that's kind of, you're seeing it more face on here. You see the kind of spiral shape. These are little dust lanes here, just like you see in our Milky Way. Here's the central bulge. Here's another spiral galaxy seen kind of face on, so you really get that kind of pinwheel effect. But again, it has a central bulge, and then this is the disk component. Again, as you can see, the disk component is a little bluer because you have active star formation. And associated with active star formation are these kind of dust trails where the stars are forming. Okay, here's a barred spiral. This one's just kind of interesting because here is zoomed out. So for a barred spiral, you see that the central bulge is kind of cigar shaped, and then kind of see those two sprinkler-like extensions. This one's just kind of cool because if you zoom in into this little box, you get another looking. So the very central bulge, even itself, contains a region that looks like another little galaxy. Here's a real classic pinwheel galaxy called the Whirlpool Galaxy, where you're basically seeing it just face on. Here's the central bulge, but because it's face on, you're really just seeing that thin disk and those beautiful dust lanes. And here's a side view. Nice to see a side view of the same thing, right? It gives you a very different perspective. It's called a needle galaxy because in a side view, it looks kind of like a needle, but really what you can see here very clearly is the central bulge, and then that thin disk. And that thin disk you see has lots of dust lanes. That's why it kind of obscures the light, just like in our own Milky Way. Those lanes of dust are associated with places where stars are forming. Nice spiral galaxy, Bode's galaxy. Again, you see that's kind of bluish where there's star formation. You see kind of orangish central bulge. One of my favorite just looking galaxies, the Sombrero galaxy.
Sombrero?
Very, very large central bulge. Okay, this is spiral type A, meaning the central bulge is really large. The spiral, the disk is kind of tightly held. So tightly held disk, very large, kind of elliptical galaxy like the central bulge in the center. Here's the other end of the spectrum. Here's type lowercase c, meaning there's not much of a central bulge at all. It's almost all disk. So this is beautiful, just thin bluish disk. You have a little bit of a central orange bulge here, but it's not very prominent. That's called the sculptor galaxy. Okay, here's a spiral galaxy. I just want you to see lots of because there's such a diverse set of different looking galaxies, and there's really too many to to show you all the pictures. I showed you that Hubble Space Telescope image where there were 5,000 galaxies, and that's just in a tiny pinprick of the sky. Here's a really nice barred spiral. So you see this bar in the center. So the central bulge is kind of cigar shaped, and then the most common thing, or the most characteristic thing, are kind of two spiral arms, one coming out like a sprinkler on this side, one on this side. And again, what you see is that bulge is kind of orange, but the spiral arms are bluer because of the active star formation. Again, when you have active star formation, you can produce those really massive stars that outshine all the others, and those are blue. But they don't live very long, which is why if you want blue spiral arms, you have to keep creating them. So it needs to be in a region where there's active star formation. Here's another barred spiral, so you can see the bar shape. There's another barred spiral, very clear kind of bar shape with the two sprinkler head arms. This one just also happens to have these little lines are pointing to a supernova that's happening. A really clear barred spiral. Why does ongoing star formation lead to a blue-white appearance? It's because short-lived blue stars outshine all the others. You're producing lots of stars where there's star formation. So you can produce some of these stars that won't live very long, but they outshine all the others into blue, type O, bluish stars. Now, lenticular galaxies are in between spiral and elliptical. So they have disks like spiral galaxies. They tend to have less gas and dust, but they don't have spiral arms. The bulge, central bulge, is fairly prominent. Here's just two examples, one side on, one from the front. And this is not as interesting because it's just an intermediate case. Here's these two examples. But they're intermediate between spirals and ellipticals. So before I let you go, let's look at some elliptical galaxy pictures. Again, the idea with an elliptical is that it's like you just took away the disk of a spiral galaxy and left that central bulge. The main difference is that there's a larger range of masses to these elliptical galaxies. They can be really, really big. They can be really, really small. They tend to be redder. They tend to have less cool gas. They tend to have less active star formation. Okay, here's a classic looking elliptical. For comparison, here's a spiral up here. The elliptical just looks like a giant fuzzball. It's more orange. Couple elliptical. You see a number in this photograph. Here's two ellipticals. There's a really, really big elliptical galaxy. you take that same elliptical and you look in the X-rays, you see this. So you're seeing lots of the gas. That's not invisible light, but it's been heated up, just showing you how big of the halo of a galaxy can extend beyond where you see. So really big elliptical. And then finally, it's just, you know, there's nothing special to create only spiral and ellipticals. There's also just irregular galaxies, but not any particular shape. Some famous ones are little satellite galaxies to our own, right? So our Milky Way has two little satellite galaxies called the small and large Magellanic Clouds, right? Originally, they just kind of looked like cloudy shaped, so they were originally called clouds. Here they are in one picture, the large and the small Magellanic Clouds. You can see them on a very dark night. Up close is the large Magellanic Cloud. As you can see, it just looks like a kind of a cloudy, giant bunch of stars. There's the small Magellanic Cloud right here. You can see a globular cluster over here. Small Magellanic Cloud. Here's another irregular galaxy. It's Barnard's galaxy, an irregular galaxy. Another. All right, and that is a good place to stop before we start talking about larger structures in the universe. We talked about stars, we talked about clusters of stars, we talked about galaxies, Milky Way, we talked about galaxies. Now we're going to talk about groups of galaxies and keep expanding outward. Are there any questions? Anything at all? Okay, everyone have a good weekend. Don't forget that there's a quiz that today is the last day to finish your quiz on the life and death of stars. Bye.
Thank you. Bye, Professor.